So this is part of the AS level for A-level chemistry. And I'm going to talk you through here today how you make a pure dry liquid in an organic preparation. So the pure dry liquid that we're going to talk about making here today is 1-bromobutane. We're going to make that from butan-1-ol. However, this preparation, this method, and all the techniques associated with it are analogous to the preparation of making any other pure dry organic liquid in the A-level chemistry syllabus. So you may well, if you're very lucky, in the examination be asked the specific one, but if you're not, the methods, the strategies, the techniques to make the pure dry liquid in this will be the same as those for any other organic liquid, even though the product itself would be different in that instance and the reactants, of course, would be different. So let's look firstly at how or why we would want to make a pure dry organic liquid. Well, when you carry out many organic reactions, most of them don't go to completion. And if you think about it, that means that you will have unreacted reactants in your final product. Now, if you're making a pure dry anything, you cannot have reactants in there contaminating your final product. You may also have catalysts in there. Catalysts can persist because remember the catalysts are regenerated during a reaction, so they will be there at the end. You don't want your catalyst in your final product. So you have unwanted products that are actually made along the synthetic pathway, and in other words, as part of the reactions that you use to make your desired product. You will have other reactants made in that pathway or as side reactions or byproducts, if you like. You need to get rid of those. And a pure dry product at the end of the day is vital for, first of all, consumer safety, okay, so your customers, and for your company's reputation. You're going to be, if you go into chemical engineering or manufacturing of chemicals, they must be made in such a way that they can be administered to patients, animals, okay, they can be used in agriculture, so they've got to be what they're meant to be. So the case study, as I said earlier, that we're going to look at, but this is applicable to many other preparations, is making 1-bromobutane from butan-1-ol. So a preparation very simply means that it must be left in a pure dry form. So what I'm going to do is I'm going to talk you through the method, but I'm also going to talk you through kind of the questions that an examiner would ask about various stages in the method, because I mean, let's face it, anybody can learn a method, but not everybody can answer questions as to why you did this or why you did that during the method. So we're going to look at this method, and as I said, as I go through it, I will talk you through the various reasons why we do X, Y, and Z. So the first thing we'll do is we're going to take some butan-1-ol, some water, and some solid sodium bromide. So we'll just kind of write this up here. We've got our alcohol at the minute, we've got some water, and we've got sodium bromide. We're going to put that into what's called a pear-shaped flask. Now we'll look at why we use a pear-shaped flask in a little minute. So anyway, that's what we've got in there. There's no reaction going on in there. Those are just mixed together at the minute. Now you may well have to do a calculation here. You might have to add a certain number of moles of butan-1-ol, and you would work that out from its volume and from its density, okay? You may be given the volume and density of it, and you may have to calculate out a percentage yield later on. Remember, mass equals volume times density, and then mass equals moles, okay? Moles times RFM. So if we've got volume and we've got density of something, we can get the mass. If we've got the mass, we can get the moles. If we get the moles of reactant, we can get the moles of product that should be made. In other words, the theoretical yield. And therefore, we can get our percentage yield. Right, the next thing that we're going to add to this round bottom flask are some anti-bump granules. And anti-bump granules, very simply, are tiny little granules that are inert. They don't take part in the reaction, but they allow for a nice, smooth boiling. You're going to be using glassware here, which is connected by very delicate joints. It's called quick fit apparatus. You'll meet it in class. Okay, but it's really important that that quick fit apparatus sticks together and stays together to prevent any gases escaping or indeed any liquid escaping. And to do that, you want a nice, smooth boiling, and that's where your anti-bump granules
At Amazon,
come into play.
discover electrifying offers.
So this is anti-bump granule, this is a boiling mixture without anti-bump granules, and you can hopefully see the really aggressive boiling that's going on in here. You can hear the bumping. So that's not what we want. This, on the other hand, is boiling with anti-bump granules. And you can hardly actually see the liquid boiling at all. It's a really smooth, controlled boiling. And we can boil this in this reflux apparatus that we're going to look at in a minute, really for essentially as long as we want. Okay? So that's what our anti-bump granules are used for, in order to make sure that that boiling is nice and smooth and the heat is spread throughout the mixture. So that's what anti-bump granules are for. First of all, to ensure that there's nice smooth boiling. But secondly, I talked about spreading the heat out. And if you think about it, you need the heat to be spread uniformly throughout a mixture. It's no different than sort of baking a cake. If I had a cake and I put it into my oven and it was cooler at the top than it was at the bottom, I don't know, let's say 100 degrees at the top and 200 degrees at the bottom, you're going to get a completely different set of chemical reactions at the top than you'll get at the bottom. So that's the reason why we have to ensure that the heat is spread throughout, because if it's not, you get what we call superheated areas or hot spots, which create different products and unwanted products. Okay, so therefore, that's what are two reasons for using anti-bump granules, and that's what they look like, sorry, on the top right-hand corner there. Right, the next thing we're going to do is we've got our anti-bump granules, okay, in here. We've got our, I'll just draw my very oddly looking shaped, pear-shaped flask. So in here at the minute we have our alcohol, we have water, we have sodium bromide, and now we're going to add to this concentrated sulfuric acid. Okay, so we're getting ourselves all set up for this reaction to occur. Right, now we have to be very careful adding the conc sulfuric acid for two reasons. Or so for three reasons. But we add it, what we would say, is with stirring and with cooling. And there's reasons for that. First of all, when I add conc sulfuric acid to water, remember there's already water in here, it gives out a huge amount of heat. It gives out so much heat that it can cause the concentrated sulfuric acid to turn into a gas, to vaporize. Now, that is the last thing you want in any lab, are gaseous fumes of concentrated sulfuric acid in the air, for fairly obvious reasons. The second thing is, if you add concentrated sulfuric acid and it gets hot, the concentrated sulfuric acid can act as a dehydrating agent. Now, a dehydrating agent will dehydrate the alcohol. So if I have an alcohol, let's take the one that we have here, which is butanol, and I add conc sulfuric acid to it, and I also have it hot, okay, which is what happened if I added it too quickly. That will cause the alcohol to turn into black sooty carbon and water. It will dehydrate it. And dehydration means that you are actually removing the elements of water from the compound. So you can see hydrogen and oxygen have actually been ripped off that butan-1-ol there, and you've got a completely unwanted set of products in this particular reaction. You want your butan-1-ol to turn into, through chemical reactions, 1-bromobutane. Well, if it's dehydrated, that's impossible, and your percentage yield will end up being minimal. The last thing is that, and if this is part of your Group 7 chemistry in Unit 1, the last thing, if you have conc sulfuric acid and heat, your bromide ions that are in here, in your sodium bromide, you want those for a reaction later. And the reason why you want those is because they will actually react with the butan-1-ol to turn it into 1-bromobutane. If the concentrated sulfuric acid gets too hot, a different reaction will occur, and your bromide ions will get converted into bromine. They will get oxidized. You can see there's a loss of electrons here. Okay? You need to avoid that reaction happening. So there's your three reasons why you want to add the conc sulfuric acid slowly and with stirring. 1, avoid excess heat vaporizing the sulfuric acid and making a corrosive mist. 2, avoid the excess heat in the sulfuric acid dehydrating your alcohol into an alkene or into carbon and water. Okay? And finally, to avoid your bromide ions, which you want to react with the butan-1-ol to form 1-bromobutane, to avoid them being oxidized to bromine. Right, next. So once this reaction starts to happen, the sodium bromide will react with the conc sulfuric acid, and that will make your reactant hydrogen bromide. Now, this is probably the first time in A-level chemistry where you haven't just gone to a bottle or a shelf and lifted a bottle off of your reactant. You've actually made the hydrogen bromide in the place of the reaction. And it is made by the reaction between the sulfuric acid here and the sodium bromide that we put into our flask, if you remember back up at the start, you put that in with the water and the butan-1-ol. That triggers off a reaction which makes hydrogen bromide. The hydrogen bromide is the reactant that will react with the alcohol to make the 1-bromobutane. We'll see the equation in a minute. Okay, so this hydrogen bromide, which is a reactant, is made in the place of the reaction. Okay, and that is called being made in situ. Okay, so instead of just going and lifting a bottle of it off the table or off the shelf, you have to make it in situ. You would tend to do this with things that are very unstable, so they may react with water or moisture or oxygen in the air. Okay, so they're very hard to store. They may perhaps they're very light sensitive, so they're difficult to store. Maybe they're extremely toxic and you just don't want to store them. It's easier to make them in situ in the place of the reaction. Now you'll notice here the other byproduct, and you'll be asked to write this equation quite a lot, is sodium hydrogen sulfate, not sodium sulfate. Do not write sodium sulfate. On occasions on the mark schemes they will not accept that. The accepted reaction for this is, our equation for this reaction is reaction 1 on the screen. So we'll mix that all together. Now we'll give it a really good shake to make it homogeneous. Homogeneous just means that at this point, if you were to look at inside your flask, you probably see that it is in 2 distinct layers. Okay? Homogeneous means you shake it all up and make it into 1 distinct layer. And the reason why we do that is because if I start heating and it's in 2 layers, it's likely to be quite difficult to control in terms of heating, even with the anti-bump granules in there. And it's much easier to get things to react together if they're mixed together in 1 homogeneous mixture. The next thing we're going to do is we're going to heat this under reflux, which is a new type of reaction apparatus to you, and we'll look at that in a wee second. But there's 2 reasons why we heat things under reflux. We'll look at the apparatus here and I'll explain why we heat under reflux. So if we look at this apparatus over on the right, we've got our flask with all of our reactants in it. Now these reactants, we've got to break the covalent bonds in them. So in here, in the alcohol, we've got to break, okay, the bonds here. Okay, now those bonds are quite strong, so they take a lot of heat. However, the intermolecular forces within this compound are relatively weak, so it will vaporize very easily. It will turn into a gas. So if I did it in a beaker in the open room, very simply, when I started heating it to get enough energy to break the bonds, the liquid would very simply evaporate off and I'd have nothing left. I'd have a room full of toxic alcohol vapors. The thing about reflux is you can heat this thing, and when you heat it, the vapors they vaporize, but they rise up and they hit the cool inside of this condenser and they condense back down again. And you can continue that boiling, evaporation and condensation really for as long as you want. Okay, and that means you reach the activation energy because you're putting loads of energy into it, and it also means that you're not losing any volatile reactants, nor are you losing any volatile products. Okay, so that's a diagram on the right hand side that you will have to be able to possibly draw, but certainly label. Okay, common mistakes are people put a bung in the top there. That is wrong. It has to be open, and they put the water in and out in the wrong places. And the other common mistake is they just leave gaps. This apparatus has to be sealed everywhere except at the top. So be careful of that. Right, next thing then, we put this into, we can just heat it and we can put our anti-bump granules in it, but that also creates a possibility of some parts of it getting hotter than others. So if you really had an experiment where you wanted to spread the heat, you can do 2 things. Well, you can do a few things actually. You can put it inside a beaker of water and use that to heat it. Okay, you would heat the water from below. Now that only works if your reactants and products are able to boil at less than 100 degrees. You could use an oil bath, okay, which will have a higher temperature, and you can boil your things at much higher temperature. Oil baths are nasty, dangerous, and messy. The oil can catch fire if you're not careful, and the boil can bubble out if you're not careful as well. So it's a bit messy. The other thing you can use is called a sand bath, and we'll look at that over in the next page. And the whole point of all 3 of those things is just to promote an even better, even boiling and even refluxing of your reaction mixture. Okay, right, when I get my HBr made, then my reaction with the alcohol here can start to take place, and I'm going to make my product, my bromobutane as it is in this particular instance. And remember, I made a byproduct here also of water. Remember, I'm going to have to get rid of that later on. As I said earlier, whenever we are doing a preparation, we're making a substance in its pure dry state. Okay, so this just is a picture of a sand bath, just to sort of show you how you get that nice, nice even heating. And sand produces a really nice even heating around that. Right, so we've refluxes. We've carried out our heat under reflux, as I said, up here on the top right-hand corner. Now what are we going to do? Because we've made our product, but it's in amongst a whole load of other things in that flask. It's by no means pure. So we've now got to get rid of our undesired side products, our undesired reactants, a whole load of things. So the first thing that we'll do is we'll distill it. We'll distill over and we'll collect our 1-bromobutane at kind of plus or minus 2 degrees around its boiling point. And when you move from GCSE, you sort of think that distillation is this holy grail of purification. It isn't really. It does give us a purer product, but there's still lots of undesired waste materials and impurities in there that we still have to get rid of. And we'll work through that process over the next few slides. So our pure crude product still has impurities in it. Okay, this is our distillation apparatus here. You'll see now we have a thermometer in it, and the bulb is always at the outlet where it meets the condenser. We'll see our condenser now is horizontal rather than vertical as it was for reflux. We'll see we now have a collection flask, which we didn't have for reflux. We also have a pressure outlet to allow, make sure there's no buildup of pressure and explosion. And again, our water is in at the bottom and out at the top. That's always the case. And always make sure all your joints are sealed, okay? You can see even in this hand-drawn diagram, everything is sealed apart from our pressure outlet down here, okay? So we'll boil across and we'll collect our 1-bromobutane over here, okay, at about plus or minus 2 degrees within its boiling point. So we've got that now. We've still got some impurities that we need to deal with. So after we finish the distillation, we've still got some impurities in that reaction mixture. So in our distillate, even though it is a purer form of the 1-bromobutane than we had in the reflux flask, we've now got to get rid of the other impurities. So let's have a look at how we go about those. So we're still going to have small amounts of butan-1-ol. We're going to have some water. We're still going to have some of the unreacted sulfuric acid from earlier. And we need to get the 1-bromobutane out of that, or maybe those things out of the 1-bromobutane, either way, to increase the purity of the 1-bromobutane. So number one, what are we going to do? We're going to add some, everything that was in the distillate, we're going to add it to a separating funnel. And to that, we're going to add some deionized water. Okay, we're going to keep our finger on the stopper. Now you can do that, or at this point you may also add some concentrated hydrochloric acid. The reason why we do that is because concentrated hydrochloric acid will do a thing called protonate the alcohol. So there's my alcohol group to begin with. There's my alcohol group now with the acid that has been protonated. And when I protonate it, I make it much more soluble in water than it was originally. So if I add water to my distillate, and then I give it a good shake up, anything that is water soluble will dissolve into the water layer. The 1-bromobutane, which is not water soluble, will stay on a separate layer. Okay? By protonating the alcohol with the conc hydrochloric acid, I make it even more soluble in the water, so even more of it should be removed from the 1-bromobutane. So, like I said, when you do that, all the water soluble impurities will make their way into the water layer, and you will have two layers in your separating funnel. So if we look at a separating funnel here, when you do this, you would have two distinct and two separate layers in it. Okay? Now, the examiner on occasion would ask you to suggest how you might work out which of those layers is actually the water layer and which of those layers is the layer you want to keep, i.e. the 1-bromobutane layer. There's two methods you can use here. One, you can simply add more water to it and shake it up, and the layer which gets bigger must be the water layer. Alternatively, you can look up densities, and whichever layer is denser will of course be at the bottom after you've given it a shake up. Now, once we've done that, we will remove the stopper from up here, and we will allow the tap to open. Now, the reason why you remove the stopper, because if you don't, what will happen is that air will get sucked in from the bottom, and these two layers will simply get mixed up again. So you must remove the stopper before you let anything out of the separating funnel. Okay, now that mixture at this point, so let's say our 1-bromobutane is denser. It is denser, by the way. 1-bromobutane is density, I think, of 1.37 grams per decimeter cubed, and the water is about 1 gram per centimeter cubed, sorry. So the 1-bromobutane layer will be at the bottom. So again, we just collect the bottom layer and we can get rid of the top layer, the aqueous layer as we would call it. Now that bottom layer with the 1-bromobutane still has tiny amounts of acid and water in it. So we've got to get rid of those. First step, we're going to get rid of the acid. And to do that, we're going to put it back into a separating funnel again, and we're going to add some sodium carbonate or sodium hydrogen carbonate. Note, you have to tell the examiner that it's the solution, not the solid. And that will neutralize any acid that's in there. If you remember, carbonate or hydrogen carbonate with acid gives you water plus carbon dioxide. Now this is good because we're going to get rid of acid. Okay. However, we're going to bring more water into the reaction mixture, the 1-bromobutane, as a impurity, but we'll deal with that in the next step. And the other thing we've got to be careful of here, we're making carbon dioxide gas, and we're making that inside a separating funnel, remember, which is a sealed environment. So we have to release that gas on occasions to make sure that the pressure doesn't build up too much. There's a specific way to do that. Okay, we invert the separating funnel and we keep our finger on the stopper to hold it in, and we allow the gas out through the stopcock or the tap at the top. The reason why we do that is because if we let it out through the stopcock at the top, we can very slowly and controlled allow that gas out. If we turned it 180 degrees from where it is at the minute, and we took the stopper off, you run the risk of, a bit like opening a shook-up bottle of Diet Coke, you run the risk of a little liquid fizzing out through that big open top. You also run the risk of the stopper, if it's under significant pressure, flying off and perhaps hitting someone in the face or anywhere. But those are the two reasons why you don't allow the gas out through the stopper, okay? And you allow it out through the stopcock with the funnel inverted, okay? Right, so we've now got rid of our acid. Our last thing that we've got to do is get rid of the traces of water plus the water that we introduced in this equation here. So this time what we're going to do is we're going to take our product out of the separating funnel again. Okay, and we're going to collect and keep the correct product based on densities. Okay, and after we've done that, then what we're going to do is we're going to add to it a few granules of anhydrous calcium chloride. Now, anhydrous calcium chloride, okay, you can use various different things, but anhydrous calcium chloride is the one on the spec, so I suggest you just use it. Either way, it has to be anhydrous. And anhydrous means without water. So this thing is put in here to absorb, to suck up the water. So it kind of acts like a molecular sponge, if you like. It attracts water and it holds it and keeps it within it. Now, the liquid at this point will be cloudy. Whenever all the water has been absorbed out of it, it will go clear. And once you've got that, and you've got rid of all the water, you can then do what we call a second distillation or a redistillation. And that will be done sort of plus or minus 1 degree within the boiling point of 1-bromobutane. And you will get now your final product of 1-bromobutane. So look just quickly at the anhydrous calcium chloride or magnesium sulfate. There are some others, but just choose one and make sure you use the word anhydrous in front of it. So that's what it looks like. It's a very dry looking particles, dry looking little grains of, I think that's calcium chloride there. And you just put it in like so, and your mixture at the beginning there should be cloudy, and at the end it should be nice and clear when all the water molecules are gone. And this is kind of how it works. If you see the blue water molecules throughout the mixture here, and we add our white particles of anhydrous calcium chloride, and you can see the blue water molecules are now trapped at the bottom and they're attracted to the anhydrous compound. You simply now decant off the liquid, which means you just pour it off and keep the solid behind very carefully and very slowly, or you can filter out the liquid. The problem with that is sometimes you don't have very much and you can lose some of it when it gets absorbed into the filter paper itself. Okay? So you need to be a little bit careful of that. And then finally, we've now got a very pure product and we simply redistill it. Okay? And that should give you your desired organic product, okay? Which you can then use for, well, whatever, it depends what industry you're working in. Okay? And that gives you your product. You need to be then able to, and after this slide, or after this slide, there are some past paper questions. I will email my students across the past paper questions and the answers on this preparation of 1-bromobutane and on some others as well, okay, to give you an idea of the sort of types of questions and answers that you might get on this particular topic. But you should at this point have a nice pure product which you can go to market with. Okay, well, I hope that helps, and thank you very much.